All right, so the first topic of this chapter is area, but not area under a curve, area between two curves. Okay, so what are we talking about? You have this function, f, okay, and then maybe you have another function, g. Right now, clearly there is an area between these two, right? So you have this. Let's say we have this integral. Maybe I'll well, okay, so I'll go ahead and say, if you have an integral, so this is 0, and let's say this is a and b, this integral from a to b of fx dx, okay? What is that? I'm going to draw this in pink. So that would be this whole area, right? And if I say, what area does this represent? The integral from a to b of gx dx, you will say, and I will do this with a light, sort of a bluish, greenish color, it's that, right? And so what do you do if you have to find the area between these two functions on or over a and b? Well, so that's an easy thing to do, right? So area A is going to be the difference between f and g. So it'll be the integral from a to b of f minus g. Now, f minus g itself is a function. As a difference of two functions, it is a function. F minus g is defined at every point, which has to do, by the way, at this length here, right? This length here for this x, the length between this point and this point is the value, this point and this point is the value of the function f minus g, it's a new function, at point x, right? So if you evaluate that, and if you integrate that function, f minus g, clearly you should have the area. So there's nothing too difficult about this thing here, assuming here that f is greater than g on at every single point of a, b, right? So this is simply, I should say, this is a1, this is a2, and so the area A is a1 minus a2, which of course is defined this way, right? And so is this hard? No. Okay, this is exactly what you think it is. And if you didn't learn this as a new section, I think you could have figured this out. All right, let's see, find the area between. Now, sometimes what is difficult is maybe, okay, to find what the x values are, the endpoints a and b. Find the area between fx is x plus 2 and gx, which is x squared, right? Of course, it helps if you can graph these functions. And so let's try to make it nice, because always it's nice to have a clearly, and accurately drawn graphs. Okay, so f of x is x plus 2. Well, that's an easy one. That's just a straight line function, right? And so I start at 2. And so it's going to be something like this. Is that okay? Yeah, that looks good, right? Recognizing that the slope is 1 and y-intercept is 2, right? The other one is slightly more difficult to graph. Let's say you have -2, 4 and -1, 1, 0, 0. This is your typical or a standard parabola. And so you can graph like this, okay? And once you do this, it's very clear what the area referred to is. Okay, it's the area of this region between these. And again, sometimes they do not give you the values like this, the a and b here. And so now, obviously, this is -1 and 2. But what happens if you are not sure, or if the numbers are not very nice? Okay, well, so the first thing you have to do is to find the intersection points. Again, for this particular problem, it's not too bad, right? Because basically you have to set f and g equal to each other, because these are the points where f and g intersect. In other words, we are looking for the 2 points where f of g and f of x and g of x are the same. And so that, algebraically speaking, means x squared and x plus 2 are equal to each other. And of course, this involves algebraic manipulation. X1 and x2, no, that's not true. X plus 1 and x minus 2 is how you factor this. And using the zero property, you can say x must be -1 or 2. And so these are the 2 intersection points. Now, which one is higher and which one is lower? This is x squared. And in this interval, f of x, this is g of x, right? F of x is bigger than g of x. So f of x, g of x, okay. And basically, this length defined for each x, the length of these red segments, okay, that is the function you're integrating. So it will be -1 to 2, and then f is higher, so x plus 2 minus x squared, and that is exactly what you're integrating. Again, this representing for each x, this expression representing the height or the length of those red segments. All right, so now we can use the fundamental theorem of calculus. X becomes x squared over 2, 2 becomes 2x, x squared becomes x cubed over 3, right? And then evaluate them at -1 and 2. The rest should be easy, right? 2 squared 2, that's 2 plus 4 minus, now 2/3 is 8. Okay, and then plug in -1. Now again, it's tricky, so be careful here, right? It's -1 squared, which is 1 over 2, minus 1. Now it's minus -1 over 3, so it's plus 1/3. Okay, so you have to be very, very careful at this point, because you don't want to mess up, at this point, right? And so let's try to do this right. And of course, talking and writing makes calculations sometimes messed up, and so I did not enter the right amount here. And that middle part is plus 2x, that would be -2 here, right? So what we have here is the 6 minus 8/3, okay? And then minus, and let's try to calculate this part here. I mean, this is just arithmetic, but this is -3 over 2. And then if you do not distribute the negative signs here, let's try to do this again. 6, and these can be added together. 6 plus 3 over 2, because negative makes it positive. And then you have minus 8/3 minus 1/3, that's 9/3, right? That's 3. Okay, so this will be 3 plus 3 halves. Okay, so this will be 9 over 2. Okay, or 4.5 if you want to use a decimal. Okay, so that is the area of the region bounded by these 2 curves or 2 functions. All right, so that's not too bad. All right, now here's another example, slightly more complicated. All right, let me go ahead and graph this more carefully. What makes this a little more challenging is the following. Let me go ahead and stop this so I can graph this. All right, so here's another question. I said slightly more difficult, and you'll see why this is. Let's say the question here is, find the area of the region bounded by the x-axis, which is what you see here. Y is equal to x squared, which is this parabola, and then y is -x plus 2, which is this line, right? So you can see these are, correctly drawn graphs. The last one, the slope is -1, and the y-intercept is 2, so it goes down. So you can see this area is sort of like this rectangular region, although it's not quite rectangular. right? And so you can easily find these points, by the way. This has to be 0 because it is where y is x squared hits the x-axis. This has to be 2 because the x-intercept of this is 2, right? I mean, set this equal to 0, and you find that x must be 2. So that's not too hard. And then there's this point, okay? So what is this point? That's the point of intersection of these two functions. So this will be x squared is equal to negative x plus 2. You can simply solve this. And you'll see this is x minus 1, x minus 2. Not quite. This will be like that. And so x is either 1 or negative 2. Now, this negative 2 is not seen here. It's actually, if you keep going here, eventually they will meet when x is equal to negative 2, but it's not a part of this picture. So we will not worry about that, right? And so this point is 1. All right. So what's the upper function? Well, the upper function, lower function is 0. Okay, so the lower limit for the integral will be 0. But you notice here, the what happens is between 0 and 1, the higher function is x squared. All right. So you have to say it's x squared minus 0. 0 is this bottom line here, right? And so what you have to calculate is between 0 and 1, you have to calculate the integral of x squared. That's this area here. Okay, so I will color code this. That is what you need to have. Now, from 1 to 2, that's still a part of the region that I am supposed to find the area for. But between 1 and 2, my upper function is going to be different, right? And that's going to be this function, which is negative x plus 2. And then, of course, goes down to 0. So that's what I have to find. So that's my blue part, or the region. And that goes from 1 to 2. And then negative x plus 2 is the top. And of course, minus 0. I know I don't have to put minus 0, but just because we are learning the, the region between two functions, maybe I should just have this 0, minus 0, just so I'm, I can indicate that I am interested in finding the area between curves, where the bottom curve, quote unquote curve, is just the x-axis. All right, so this is from 1 to 2 of negative x plus 2. And in the end, we have to combine these two things, because I have to add up the red area and the blue area. That sounds like politics, but all right. So the first one is easy. X third over 3, evaluate it from 0 to 1. So this will give you 1/3, which you already knew because we did this maybe as a very, very first example of the integrals. And then the second one, negative x squared over 2 plus 2x from 1 to 2. And this is when you plug in 2, you have 2 squared over 2 with a negative sign. And then 2 times 2 is that. And then if you plug in 1, you get that. All right, so this is negative 2 plus 4, and then minus 2 plus 1/2. And of course, these will cancel. It's 1/2, right? And therefore, the area, the total area is 1/3 plus 1/2. And that's, of course, 2 plus 3 on the top, 6 in the denominator. And the answer is 5/6 unit square, right? So this part is 1/3, and this part happens to be 1/2. Of course, that's 1/2 because that's half of that 1 by 1 triangle square, right? So you could have used geometry to calculate the second part, the second integral. All right, so that, and then you have a few more problems to do on your assignment. Now, I wish, and maybe you would wish, this is the end of section 1, but there is something else that's happening. Now, see, notice here, all right, we have been using x as our independent variable because that's what we have always done. But it turns out an area like this, which I will do again in part 3 of section 1 lecture video, but there's a way to make y as the independent variable. And we can integrate this kind of area with respect to y. And then the problem sometimes becomes simpler, all right? Now, using y as the independent variable could defy your common sense. And it may be very unfamiliar, and it may make you very uncomfortable. It certainly did when I was learning this, but try to get used to it, okay? There's nothing magic about x, right? Y could easily also be an independent variable. So this is the approach we're going to take. And I will go back and revisit this problem and maybe another problem in the third section of in the third part of section 6.1.